Alright, so today we're going to be talking about an extremely powerful power series known as the Taylor series. And before I get into defining the Taylor series, I'm going to give you some intuition behind what this infinite series really does. And so let's just start off with the intuition. So what we want to do is the first problem asks us to construct a polynomial that looks like p of x is equal to a0 plus a1 times x plus a2 times x squared plus a3 times x cubed plus a4 times x to the power 4 that matches behavior of the natural log of 1 plus x at x is equal to 0 for the first 4 derivatives. So what we want is we want this polynomial to have the same values as the natural log of 1 plus x at x equals 0 and its first 4 derivatives. So we know that p of 0 must be equal to the natural log of 1 plus 0 because we need p of 0 to have a matching value. And so that should just be equal to 0. And then we know that the derivative of d dx of the natural log of 1 plus x is equal to 1 over 1 plus x, and the value of that at x equals 0 is simply equal to 1, which should be equal to p prime of 0. Now, the derivative of 1 over 1 plus x is equal to negative 1 over 1 plus x squared. And at x equals 0, its value is simply equal to negative 1. So that should equal p prime, double prime of 0. Then we have d of dx of negative 1 over 1 plus x squared is simply equal to 2 divided by 1 plus x cubed. And the value at x equals 0 is simply equal to 2. And that is the third derivative of the polynomial as well. And finally, we have d over dx of 2 divided by 1 plus x cubed is equal to minus 6 divided by 1 plus x to the power of 4. And at x equals 0, that evaluates to negative 6, and that should be p of the fourth derivative of the polynomial. And now that we know how how our polynomial behaves at each value, we know that if p of 0 is, if p of 0 is equal to 0, that means a0 should be equal to 0. P prime of 0 is simply equal to a1 plus 2a2x plus a3 or 3a3x squared plus 4a4x cubed. And notice how when x is equal to 0, all of these other terms don't matter because they'll be zeroed out, and hence we get that a1 is equal to 1, negative 1 I meant. Then we also so a1 is equal to negative 1. Similarly, p double prime of 0, so okay, let's box out our results. So a0 is equal to 0, a1 is equal to or a1 is equal to 1, sorry, because we're equating to this. Now, p double prime of 0 will simply be equal to, p double prime is equal to 6, or 2a2 plus 6a3x plus 12a4x squared. And therefore 2a2 is equal to negative 1, and therefore a2 is equal to negative 1/2. Now let's continue over here. So p triple prime is 6a3 plus 24a4x. And so 6a3 is equal to 2, therefore a3 is equal to 1/3. And finally, we get 24a4 is equal to negative 6, and a4 is equal to negative 1/4. And so the polynomial that satisfies our constraints is p of x is equal to a0, which is 0, so I'll just ignore that, times a1 plus, or a0 plus a1 times x, and a1 was 1, and so x, we have just x, and then minus 1/2 x squared, plus 1/3 x cubed, minus 1/4 x to the power of 4. And so what we constructed right here is actually known as the fourth order Taylor polynomial of the natural log of 1 plus x at x is equal to 0. So just trying to deconstruct all these terms. So the fourth order just comes from the fact that like our highest degree is x to the power of 4. And the fact that we were saying that we're centered at x equals 0 meant that whenever we're calculating the derivatives of all our terms, we were plugging in the value of 0, and that was what was most interesting for us. We're basically centering our polynomial at the point 0. We could have centered it at another arbitrary point c, and in that case, we would have had to calculate like p of c if we wanted our polynomial to have matching behavior to this original function at that other point. So that's that part. And then natural log of 1 plus x is that function that we were trying to emulate the behavior of. And Taylor polynomial is like this method that we have used to calculate the resultant polynomial that we got over here in the bottom is called the Taylor polynomial. And we'll get more into the general formation of the Taylor polynomial, but I think the most important thing for now is to see that basically what we did was we wanted a polynomial that kind of emulated the behavior of this function, and the emulation sort of started at x equals 0. So at x equals 0, we would have a perfect match of the function, and as we kind of move away from x equals 0, we would not be perfectly matching the natural log of 1 plus x, but this polynomial kind of estimates how much 1 plus x, how much the logarithm of 1 plus x kind of behaves like. And remember when we were talking about linearization, we were kind of talking about the fact that we had some arbitrary function over here, and essentially what we're doing is we're centering at some point. And so the linearization kind of told us that we want to find a linear estimate of a function at a particular point. And so if this was point C, then we would want the matching value. So like whatever polynomial we would have estimating our original function would have p of c equals whatever the f of c is. So p of c would always equal to f of c. And then we would have our first order linear estimate. And we did that by first finding what f prime of c was, and that would serve as our slope, and that would be our only sort of estimate. And over here, that's the same thing we did. Our first degree, or our first derivative at that particular point we're centered at matches whatever the first degree derivative is of the natural log of x. But we're forming a fourth order estimate over here instead of just a linear estimate. So you can kind of imagine that's what we're doing with this Taylor series. We're kind of estimating whatever function we're finding the Taylor series of centered at a particular point. So close to this value, we're going to have better estimates. And also as we increase our degree, so as we go from, well, the linear estimate, or let's just like the most trivial example is like if we just have a point estimate, we're only going to have a matching value for that point. And as we move away from the point, we're not guaranteed to match it. But as we add more terms, so as we increase the degree, we're probably going to be better emulating the original function. And now we're just written the original function as the summation of polynomial terms. And so that's the most powerful thing about the Taylor series, that we have sort of taken a complex function and now we're making it into of um, polynomial terms. And if we just kind of truncate it at a finite sort of degree, then we are forming an estimate of the original function, and now we have a polynomial estimate, which kind of helps us in many applications when having complex functions such as natural logarithms or even like trigonometric functions is kind of unfeasible. So let's just get more practice with this sort of idea. Let's construct the power series for the sine of x at x equals 0. So now this is the new function we're worried about estimating. So from now on, I want you to think about constructing like a Taylor series as trying to estimate the original function. So we're trying to estimate sine x at x equals 0 with a 7th order polynomial. So the first thing we want to do is find out the values of sine and its derivatives at x equals 0. So we know sine of 0 is equal to 0. The derivative of sine is simply cosine of 0, which is equal to 1. So this is the 0th derivative. This is the first derivative. The second derivative is minus sine of 0, which is equal to 0. The third derivative is minus cosine of 0, which is equal to negative 1. The fourth derivative is sine of 0, which is equal to 0. And now you can see that like our trends will just continue. So I'm just going to write 5, 6, 7. And so because the pattern continues, we just have periodic derivatives. So it'll just be 0, 1, 0, negative 1. And so if we were to construct the polynomial similar to how we constructed it before, we noticed how the derivatives became the coefficients, and as we increased our degree of the x, so if this was like the nth degree, because to the way that we constructed the polynomial is we basically were only seeing what that coefficient at the derivative with the 0th term would be, and that's only when we have taken the nth derivative. So at the nth derivative, we would get whatever coefficients associated with this nth term to be isolated, and therefore what would happen is that our original coefficient would be that original coefficient divided by n factorial. And if you kind of don't see this, I would advise you to look back at that example and see why this makes sense. And so with this fact, we don't have to go through the manual work of actually finding the derivatives, and we can simply plug in these values that we have and to the coefficient and associate the corresponding x term. And so we get P7 of x is equal to 0 plus 1 divided by 1 factorial, which is just 1, times x, plus 0 divided by 2 factorial times x squared. And then we get minus 1 divided by 3 factorial times x cubed, plus 0 divided by 4 factorial times x to the power 4, plus 1 divided by 5 factorial times x to the power 5, plus 0 divided by 6 factorial times x to the power 6, minus 1 divided by 7 factorial times x to the power 7. And simplifying by removing all of our 0 terms, we get x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial. And that's our 7th degree polynomial estimate of our original function. And this method of constructing our power series is known as the Taylor series. So this is our 7th degree Taylor series. And the idea is, if you can kind of notice, like, I would really highly suggest you guys to compare the graph of sine x. So we have sine x kind of looks like this, right? I would highly suggest you guys to compare the graph of sine x with each of these terms concatenated. So we know that the first degree estimate of sine x is simply y is equal to x, right? That's just like that's just from, like, you can get that from linearization as well. You have sine of 0 plus f prime of 0 times x, right? Because we're centered at 0, and so that would kind of look like just that linear function we have. And so we would get the first degree kind of looks like this. And so around values of close to 0, our first degree estimate follows pretty closely to what sine x is. But as we kind of trend outside of 0, as we get into intervals further and further away from 0, this estimate's really bad, right? So I mean, if I'm trying to if I use sine x as an estimate for, if I use this line y is equal to x as an estimate for sine x for, this value 2 pi, I would expect, well, sine 2 pi is equal to 0, but y of 2 pi is equal to 2 pi. And so my error is really large for this first degree estimate when I move outside of a small interval around 0. But as I increase my degrees estimate, so then, like, what I can't really draw it too well here, but if you were to draw it on like a graphing calculator or graphing tool like Desmos, and you were to draw this third degree estimate, you'd see that not only do you have a better representation of sine x, it would so what it would kind of look like is, with the third degree estimation, you'd have a wider interval around you'd have a wider interval around a third degree estimate would look something like this, right? Where you'd have a wider interval around x is equal to 0, where sine x where your polynomial represents sine x better. So not only the interval of estimation increases, where x minus x cubed divided by 3 factorial better estimates sine x, you also so what I was saying is, you not only can use this estimate for a wider interval, it also estimates sine x better because of the fact that your polynomial better represents sine x at a wider interval. And so that was the third degree estimate. And if you were to add up that fifth degree estimate, so if I were just to take the color yellow, so my fifth degree estimate has all of these terms, then your estimate would look something like this. So now you've once again widened the interval around x equals 0, where the polynomial better represents what sine x actually looks like. And you can kind of imagine, as we were to keep increasing this degree of estimate, so like we've seen a pattern where higher degrees of this Taylor polynomial better estimates the original function. You can kind of imagine that as we were to take the infinite degree of our Taylor polynomial, we would perfectly estimate the original function. And that's true. Because of the fact that as we take higher and higher degrees of our Taylor polynomial, when we do that, we continually better estimate the original function around the interval that we are taking our Taylor polynomial at. At the infinite degree, we perfectly estimate what that original function is. And I think, like, that fact is the most key thing, and it's why this whole idea of a Taylor series is so powerful. Because in the end, if you look at it, it only took us we only needed the behavior of a function at one point. And with that, we can reconstruct the original function at the infinite degree Taylor polynomial. So all it took was just one point and how its derivatives, like how its infinite derivatives kind of behave at that one point. But just that information allows us to basically now reconstruct our original function without actually ever knowing what that function was. So let's just say like I didn't give you that function was like sine x, but I gave you all of these facts, right? I gave you these derivatives. And these derivatives alone is enough information for us to arbitrarily reconstruct sine x. And even if we don't want to fully reconstruct sine x, and we only want to estimate sine x to a good degree around the interval, so like in here we're estimating sine x around x is equal to 0, it gives us the power to now re-express sine x as a polynomial estimate around x equals 0. And if we want a larger and if you want to, and this sort of like estimation application is very important because now we have like two choices. If you want to better estimate the original function at a larger interval around x is equal to 0, we just take higher order Taylor polynomials, and we know how to construct that now. Whereas if we only want like a rough estimate around a very small interval, we can take a simple polynomial to estimate our function instead of having that big complex function and having to reason with it. So I hope you guys kind of understand how the Taylor series allows us to basically re-represent a complex function into a summation of increasing degrees of polynomials. And as we increase the degree of the polynomial, we're better able to estimate the original function at a wider interval around whatever center we chose. And also, we only need one point and how that function behaves and its derivatives behave around that one point to be able to fully reconstruct the original function. And so given all this intuition, now let me formally define what a Taylor and Maclaurin series is. So Maclaurin and Taylor series. So a Maclaurin series, so a Maclaurin series is just a Taylor series generated by f at x is equal to 0. So what this is saying is that a Maclaurin series is just a special type of Taylor series where our center is 0. And because like having center at 0 kind of simplifies a lot of things, that's why we specially have a like designated Maclaurin series. But a Taylor series is a general series where your center can be anything not just constrained to 0. But let's talk about the Maclaurin series first. So this is the Maclaurin series. So this says that let f be a function with derivatives of all orders throughout some interval containing 0, then the Taylor series generated by f at x equals 0 is f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial. And hopefully you guys are seeing how, like, the intuition behind why this was the Taylor series, like, why you have these n factorials. You guys see that intuition from the first two problems that we did of how we were trying to estimate into a polynomial. And so this is simply defined as the sum of k equals 0 through infinity of f to the kth derivative at 0 divided by k factorial times x to the k. And so this Maclaurin series allows us to basically form a polynomial estimate of any function. So this is called the Maclaurin series generated by f, and the partial sum Pn of x is simply equal to k is equal to 0 times n of f of the kth derivative divided by k factorial times x to k. So this just says that now we're cutting off at some value n, and that helps us get like the nth up to the nth term Maclaurin series of f. And in other words, this is the Taylor polynomial. So this partial sum represents the Taylor polynomial of order n, and this n order just comes from the fact that we've used n different derivatives, and we're trying to guarantee that the first n derivatives match the first n derivatives of the actual function. Alright, so that is Taylor polynomial of order n for the function f at x equals 0. And so what's the Maclaurin series and what's the Taylor series? So the only difference between the Maclaurin series and the Taylor series is the Taylor series talks about us centering at anything, like for any general a. So all we have to do is just like a Taylor. So when I talk about Taylor series, I just have to cancel this out. So a Taylor series is a Taylor series generated by f at x is equal to some value x is equal to a. So we're centering at some value a. And essentially, basically what we're doing is instead of f being a function with derivatives of all orders throughout some interval containing 0, it's now some interval containing a. And a can obviously be 0, right? Because a is just some constant. And so just replace all of these with a, and that will give you the general Taylor series centered at an arbitrary value a. Alright, so that's the only difference between the Taylor series and the Maclaurin series. The Maclaurin series is just like a specific Taylor series where we're centered at x equals 0. And that's the only reason we have a specific name for that. Otherwise, like a Taylor series is just like any series with any sort of center, not just 0. So let's just do some problems. Find the fourth order approximate of y is equal to cosine 2x. So this is literally just applying our Taylor series formation that we saw. And so we need the first four derivatives of cosine 2x, right? But remember that like we're already kind of given what our we need the first four derivative of cosine 2x. And that's one way that we could calculate the Taylor series. But let's say we're given that the Taylor series of cosine x is equal to 1 minus x squared divided by 2 factorial plus x to the power 4 divided by 4 factorial and then continuously times negative 1 to the n of x to the 2n divided by 2n factorial. So if we're given this, can we use something about this equation that we're trying to estimate in order to find the fourth order approximation? Can we use this fact and hopefully use it in a way that helps us prevent that stops us from needing to do the work to calculate all the derivatives? And the answer to that is yes, because we're given the Taylor series approximate for cosine x, and we're trying to find one for cosine 2x. And this is the Maclaurin series of cosine x because the center is 0. And when we want to find cosine 2x, all we can do is just plug in 2x, right? So the estimate for cosine 2x will simply be 1 minus 2x squared divided by 2 factorial plus 2x to the power of 4 divided by 4 factorial plus negative 1 to the n times 2x to the 2n divided by 2n factorial. And notice how knowing this original series made it really easy to find this modified to find the series representing the modified function, because 2x is just arbitrarily multiplying a constant by x, and we can do that over here because this is completely valid in the rules of a function, right? If you have f of x is equal to some value 2x, then f of 2x is simply equal to 2 times 2x, and that's all we did over here. And so yeah, that's how we can get the Maclaurin series representing cosine 2x, and the original problem said to find the fourth order approximate, and so we just want to take these first three terms. So we get 1 minus 4x squared divided by 2 plus 16x to the power 4 divided by 4 times 3 times 2. And so 1 minus 2x squared plus this becomes 4, and then we can cancel out a 2, so 2 over 3 times x to the power 4. So that's a quick way to find out the polynomial approximate of cosine 2x. Now let's do one last problem. Find the Taylor series generated by f of x is equal to e to the power of x at x equals 2. So now we have for the first time, we have a non-zero center. And so the first thing we can do is crank out the derivatives. And so we have f of 2 is equal to e squared. And since f prime of x for this function is just e to the x, that means every single power of, or every single derivative of f of x at 2 is simply equal to e squared. So fn of 2 is equal to e squared. And so we know that the formula for the Taylor series is simply the sum from k is equal to 0 towards infinity of f to the kth derivative at our center, and our center is 2 in this case, divided by k factorial times x minus 2 to the power of k. And so plugging in what we had for this value, we can simply get the sum from k equals 0 to infinity of e squared times x minus 2 to the power of k divided by k factorial. And that's it. That is our Taylor series generated by f of x is equal to x e to the x. Let's do one last problem. And this problem asks us to find the third order Taylor polynomial for f of x is equal to 2x cubed minus 3x squared plus 4x minus 5. And so notice how this function for the first time is a polynomial function, and we're asked to find a third order Taylor polynomial. So we're finding a third order function for this function, and the first one is centered at x is equal to 0. And so, like, notice how all our terms are already written as increasing degrees of x, and we don't have it in like, well, it's like in x minus c form where c is equal to 0. So this f of x that we already have is already the third order Taylor polynomial for our original function. So that means p3 of x is simply equal to 2x cubed minus 3x squared plus 4x minus 5. And this should make sense, right? Because not only do we have it in a matching form already, where all of our x's are not followed by like a minus c that's non-zero, but we kind of expect the third order Taylor polynomial to perfectly match our original function, because our original function is also a third degree function, and if we have 3 degrees in our Taylor estimate, then we should have a perfectly matching polynomial. So hopefully those two lines of argument kind of convinced you why our third degree order Taylor polynomial is the same as our original function. The next one says we want to be centered at x is equal to 1. And now for this one, we'll have to do a bit more work. And in fact, we'll have to evaluate all our function's value at at x is equal to 1. So f of 1 is simply equal to 2 minus 3 plus 4 minus 5. That is negative 1 minus 1, which is negative 2. F prime of 1 is equal to 6x squared minus 6x plus 4. And then at 1, this is 6 minus 6 plus 4 is 4. F double prime of 1 is equal to 12x minus 6, and that's simply equal to 6. And then our last one is f triple prime of 1, which is equal to 12. So that's just equal to 12. And using our definition of what a Taylor function or Taylor polynomial is, this is using these facts, we simply get our Taylor polynomial centered at x equals 1 is negative 2 plus 4 divided by 1 factorial, which is 1, times x minus 1, plus 6 divided by 2, which will give us 3. So 3 times x minus 1 squared, plus, where was I? Yeah, 12. 12 divided by 3 factorial, which is 6. So 12 divided by 6 is 2, plus 2 times x minus 1 cubed. So although this function looks different from our original f of x, if you were to even do out the work of simplifying all these terms out, you'd get that both of these functions are equal. And I mean, another way you can check that these two are equal is just use a graphing tool like Desmos and graph out this bottom function and this top function, and you'll see how both of them are equal, and which makes sense, right? Because our Taylor series is a way of, or Taylor polynomial is a way of estimating our original function, and our original function is already a third degree function, and we're saying find a third degree estimate of a third degree function, and so you'd expect the third degree estimate to fully and correctly estimate our original function. And when you just center it at another value, you're just kind of representing it in these like forms of like x minus 1. So you're kind of you're reshifting your like basis through which like your field of view, if that makes sense. But besides reshifting, it's not doing anything else. Well, if it wasn't a perfect estimate, then around the when you center at a particular point, around that point you'll have stronger estimates than around other points away from that particular point. So in this case, your center does not really matter. But if, for example, I was taking a second degree estimate, I would only use these first three terms, and you'd expect that a second degree second degree Taylor polynomial centered at x equals 1 has a better estimate of like the value um, at x equals 1 than the second degree polynomial, which is this, centered at x equals 0, because now you're kind of further away from x equals 1. So hopefully that kind of makes sense of like why centering helps us. It just kind of reorients our frame around which we want stronger estimates. And as we increase the degree of our Taylor polynomial, we just get better estimates in general. And we're just doing a better and better job of reshaping and re-estimating our original function. So yeah, the Taylor series is a very powerful series, and it basically helps us form the estimate of the original function that we're trying to form the Taylor series of. And before ending, I'm gonna give some common Maclaurin series. And the reason for this is, remember that cosine problem where we had how cosine x looked like, and that helped us estimate cosine 2x. And so there's like a common Maclaurin series, and that can help you do problems about Taylor series in much quicker way. So the 1 over 1 minus x is the series that is represented by the sum from n is equal to 0 to infinity of x to the power of n, and this is only for when the absolute value of x is less than 1. Similarly, 1 divided by 1 plus x is equal to 1 minus x plus x squared plus minus x to the n. That's the same as the sum from n is equal to 0 to infinity of negative 1 to the n times x to the n. Again, this is for that. We saw this, e to the x is equal to 1 plus x squared divided by 2 factorial plus x to the n divided by n factorial. I'm not going to write out the summations anymore because you guys can derive that. Sine x is equal, or actually I'm just going to write the summations because that is much more compact. N is equal to 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. Cosine x is equal to 1 minus x squared, or okay, I said I'm not going to write out the, is equal to the sum from n is equal to 0 to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. And notice how sine and cosine are very similar, and that's just because, the derivatives are basically alternating. Natural log of 1 plus x is equal to sum of n is equal to 1 to infinity of negative 1 to the n minus 1 times x to the n divided by n, and then this converges on then equal to 1. So this also has a particular range where it converges, and then finally tan inverse of x is equal to the sum from n is equal to 0 to infinity of negative 1 to the n x to the 2n plus 1 divided by 2n plus 1. And if you guys don't want to use these formulas, then they're pretty easy to derive on your own as well. You just follow the first principles from the definition of a Taylor series or a Maclaurin series. But hopefully these are some of the most common functions that you'll see, and most of them are just like translations of these functions. And so hopefully having the Maclaurin series for these basic forms of these functions help you with future problems when you see other, for example, like tan inverse of 2x, you just plug in 2x here and you're done. So yeah, that's Taylor series. It's a very important topic, and hopefully you guys kind of understood it.